Hi, this is a continuation of our series of videos on inductors and capacitors. And want to talk briefly about the International System of Units. I've included a link below for an article about that. And from that system of units, we can learn a lot about what goes on with capacitors and inductors. Now, in the last video, we derived these two equations. This is for the energy stored in a capacitor, and this one is for the energy stored in an inductor. When I say stored, you can't store energy in an inductor very long because of its resistance, unless you have access to superconductors. So at any rate, in the International System of Units, energy is defined as joules, which is given the symbol J, and a joule is equivalent to a watt for a second. Now, a watt is equal to a voltamp, so a joule is also a voltamp second. Now, a coulomb of charge is an amp second. So right here we have an amp second. So we can also say a joule is a coulomb volt. Now, the unit of flux, Weber, is a volt for a second. And here we also have a volt second times an amp. So a joule is also a Weber amp. And now we can also connect this to the mechanical world. Here we're basically in the electrical world, but a joule is also equal to the force of a Newton operating through a distance of a meter. So a joule is also a Newton meter. Now, these two statements here tell us that if I apply an amp for a second to any capacitor, I'll be putting into it a charge of a coulomb. And if I apply a volt for 1 second to any inductor, I'll have a Weber of flux. Now we can sort of double check some things here and see what's actually going on with the energy storage in these components. Now, the unit for capacitance is the farad, and a farad is a coulomb per volt. So we can put this in place of the C in this equation. And when we do that, the voltage cancels out one of the voltage squared here, and we get the energy is charge times voltage over 2. So it's not just the charge that determines the stored energy, but the voltage that that charge is at. Now over here, we have henries in this equation, which is a Weber per amp. So we can stick that in this equation in place of L, and we have energy is 1/2 of a Weber per amp times amp squared. We get cancellation there, so the energy is a Weber of flux times an amp of current over 2. So the energy is not totally in the flux. It also depends on the current that is generating that flux. So these are another way of visualizing what's really happening. This will give you the numerical value of their energy with the common things. You might know the capacitance and you can measure the voltage. And here, if you know the L, you can measure the current to calculate the energy. But the equations don't really give you a feel for what's going on. My goal here is to give you a different perspective on LC as components or as phenomena. This is a 0.5 microfarad capacitor that's good for 400 volts. So that's capacitance as a component. Here's a 100 microhenry inductor that's good for 4 amperes. So we see capacitors are generally rated in volts, inductors are generally rated in current. So that's components of L and C. Now right here is a 1/2 microhenry inductor. So this is a 1/2 microhenry capacitor, microfarad capacitor. So you can see how grossly different they are. Now we can also have capacitance between wires. These wires have a projected area and a distance, and there's air between them. That's basically a capacitor. So a straight wire has inductance and it has capacitance to other objects. Even there's capacitance between here and the wiring in this room. So there's capacitance that's not a component like that, and there's inductance that is not necessarily a component such as that. So let's go outside and take a look at something that'll help us to understand this better. The power for the device that you're watching this video on most likely came over power lines like these. These wires have an inductance of approximately 1 microhenry per meter. There's a capacitance between the wires of 0.03 microfarad per 1,000 meters. Now that doesn't sound like very much capacitance, but the voltage between these wires is 345,000 volts at 60 hertz. That calculates out to about 400 amps, but will flow through this capacitance between the wires for each 100 kilometers of length. And that can add up to a lot of current over the typical lengths of power lines like these. To give you a rough idea of the size of things up here, those birds are turkey vultures, which have a wingspan of up to 6 feet. Here we see the 345 kV transmission line coming down into a substation on the edge of town. Transformers in the substation reduced the 345 kV down to 13.8 kV for local distribution and to 69 kV for distribution to smaller substations in town. At these smaller substations, the 69 kV is reduced to 13.8 kV for distribution to customers near these substations. The set of wires at the top of these poles is at 69 kV. They can be seen going left towards a small substation. The lower set of wires connect to pole-mounted transformers that reduce the 13.8 kV down to 480, 240, and 120 volt, which then connects to businesses and houses. A transformer is just an iron core inductor with multiple windings. These are capacitors, which can also be seen mounted on utility poles. These are used to cancel out some of the effects of all the inductance in the wires. They are called power factor correction capacitors. The purpose of showing all this high voltage stuff is so you can see that inductors and capacitors are not always small components mounted on circuit boards. Let's talk about the terminology used in this field. Resistors, capacitors, and inductors are classified as passive components. That is, they don't amplify or do switching functions. The capacitor and inductor are called reactors, and their property is reactance. Of course, the property of a resistor is resistance. And the symbols used are R for resistance, X sub C for capacitive reactance, X sub L for inductive reactance, and they all have the units of ohms. Now we can have combinations of the three in a circuit, and when we do, the property is called impedance, and that's designated by the symbol Z or Z, and again the units are ohms. Now that we've covered the terminology, we can look at capacitors and inductors as circuit components. Here's our setup. We have an oscillator putting out a sine wave AC signal, and we have some inductors and capacitors here, and there's resistors there as well that we're going to look at with our oscilloscope. And there's a trace, and we'll be looking at the relation between voltage and current with inductors and capacitors. Okay, here's our setup for inductors. We have a resistor in series with an inductor that's driven from an oscillator. Now the values here don't matter. The oscillator frequency doesn't matter. All we're going to look at is the waveform across the resistor and across the inductor. The current goes through both components. So the voltage across the resistor is equivalent to the current through the inductor. And we will send that signal to one channel of the oscilloscope. And then we will look at the voltage across the inductor on the other channel of the oscilloscope. And by the way, I don't think I ever mentioned why the symbol L is used for the inductors. And of course, as we mentioned in earlier videos, I is reserved for current. But there's a physicist named Heinrich Lenz, and he's responsible for Lenz's law, and so traditionally L has been used for the inductor. Now when we look at the two channels of the oscilloscope, here I took a photograph. It's easier to look at than the actual screen. The larger waveform is the voltage across the inductor. The The smaller waveform is the voltage across the resistor, so that's equivalent to the current through the inductor. Now notice the phase difference. When the voltage is at its peak, the current is crossing zero. So the voltage reaches its peak before the current does. So the terminology for that is the voltage is leading the current, and the shift is exactly 90 degrees regardless of the value of the inductor or the frequency. That shift is always the same. Now our setup for the capacitor is the same. We have the oscillator driving current through the resistor and the capacitor. So the voltage across the resistor is telling us the current waveform, and the voltage across the capacitor is the voltage across the capacitor. So this signal goes to one channel of the oscilloscope, and the voltage across the capacitor goes to the other channel. And here I've taken a photograph of the scope trace, and notice here that the current reaches its peak before the voltage does. So when the voltage is at its peak, notice the current is crossing zero. So in this case, the current is leading the voltage. And again, it doesn't matter what frequency, it doesn't matter what the value of the capacitor is. When it's a sinusoidal waveform, this 90-degree phase shift is always the same. Now those phase shifts will become important as we go on talking about inductors and capacitors. And there's a saying here that can help you remember the relationship between the voltage and current. And that little helper is Eli the Iceman. And this will help you remember that in an inductor, E leads I. And in a capacitor, I leads E. So here is the statement in words: voltage leads current. And it's also the equivalent to say current lags voltage. So now in a capacitor, current leads voltage, which means voltage lags current. So to help you remember this, just remember Eli the Iceman. Well, we saw earlier how reactors, that is, inductors and capacitors, produce a 90-degree phase shift between the applied voltage and the resulting current. Next, we'll see how to calculate the reactance of inductors and capacitors. Knowing the reactance then allows us to calculate the current that results when a known voltage is applied. Here's our standard Ohms Law formula, and the same form applies for reactance and impedance. That is, the current is the voltage over the reactance or the voltage over the impedance. Now the capital letters indicate steady state conditions. In the case of resistance, it doesn't matter whether it's DC or AC. The same formula applies. But when we're dealing with capacitors and inductors, we're using a sinusoidal AC waveform at a given frequency. So now the reactance of an inductor is given by this formula, J omega L, where omega is 2 pi times the frequency in hertz, and J is the imaginary, the square root of -1. I've attached some links to complex math if you're not familiar with this concept. Now, in math and other branches of physics, the symbol I is used for this imaginary, but in electrics, I is used to indicate intensity of current, so the letter J is used instead of the letter I for the imaginary. So, again, X sub L is the imaginary J times omega L. Capacitive reactance is given by 1 over J omega C. Now here the L is given in henries, and the capacitance C is in farads. Now if J is the square root of -1, that means J squared must equal -1. Now it turns out our imaginary J is just a way of indicating a 90-degree phase shift, which we'll see graphically here in a few minutes. Now let's do a little manipulation here. We said X sub C is 1 over J omega C. If we multiply top and bottom by J, we end up with J over J squared omega C. And remember, we said J squared is equal to -1. So we end up with this formula here. X sub C is equal to minus J over omega C. Now X sub L is J omega L, and X sub C is minus J over omega C. And this minus was hidden from us here. So the capacitive reactance is negative of inductive reactance. So X sub L, if we put in 2 pi f for omega, X sub L is J 2 pi fL, and X sub C is minus J over 2 pi fC. So let's go to a graphical representation of these to understand them better. In mathematics, this is called the complex plane. The horizontal axis is called the real axis. The vertical axis is called the imaginary axis. In our application, we are going to plot ohms on the complex plane. Resistive ohms, or real ohms, are on the horizontal axis, and reactive ohms are on the imaginary axis. Here we are showing a series RLC circuit. Now the first thing that you may be wondering is what the heck are imaginary ohms? Note that Ohm's law applies to real resistive ohms and to imaginary reactive ohms. The higher the ohms, the lower the current for any applied voltage. That's true of a real resistor or in the case of reactors. At this point, real and imaginary ohms behave the same. When current passes through real ohms, however, power is dissipated as heat, according to ohms times the current squared. There is no power dissipated in reactors. In inductors and capacitors, the current and voltage are 90 degrees out of phase. Remember Eli the Iceman. So for part of the cycle, energy is put into a reactor and is then returned to the circuit over the next part of the cycle. For this example, the frequency and the value of L and C were selected to give us 3 ohms in both cases. And we've plotted it here with a 4 ohm resistor. If we were to pass 1 ampere through our circuit, we would get 4 volts across the resistor and 3 volts across each of our reactors. The voltage across the inductor would lead the voltage across the resistor by 90 degrees. The voltage across the resistor is in phase with the current, so this means that E leads I by 90 degrees in the inductor. The 3 volts across the capacitor is shifted 90 degrees, lagging the resistor voltage, and 180 degrees lagging the inductor voltage. Now note that these ohms have arrowheads on them, and this is because they are actually vectors. They not only have magnitudes, they also have directions. These vectors can be imagined to be rotating counterclockwise around the 0 point at the applied frequency. These rotating vectors are called phasors, and they have been around for a long time, long before Star Trek. So set your phasors to stun. This is a phasor plot for an RL circuit, a resistor and an inductor in series. The phasors are added just like vectors. Here we have our 4 ohm resistor and our 3 ohms of inductive reactance. Now I purposely picked these values so we have a nice 3, 4, 5 right triangle. Now the combination of resistance and any reactance is called impedance, and this line here represents the impedance of the RL circuit. Note that the impedance also has a direction, and this angle theta tells us the direction of that phasor impedance. Now here's the formula for the magnitude of the impedance. It's the resistance squared plus the reactance squared, and you take the square root. This is the Pythagorean theorem, and we end up with an impedance of 5 ohms, and the angle theta is the inverse tangent of the reactance over the resistance. And in this case, it's approximately 37 degrees. So the angle theta tells us that the voltage across the impedance leads the current by the angle theta, or 37 degrees. Okay, here's the phasor plot for an RC circuit. In this case, the reactance is negative from our formula here. And again, the impedance is the square root of the sums of the squares of the sides. Again, that's the Pythagorean theorem. So we end up again with 5 ohms of impedance, the magnitude. Then the angle, theta, which tells us the direction of the impedance is the inverse tangent of the reactance over the resistance again. And in this case, we end up with approximately minus 37 degrees. Now, in this case, the phase shift is negative, and that tells us that the voltage across the impedance will lag the current by the angle theta. Okay, here we have an RLC circuit, and this time we've selected the capacitance so that the capacitive reactance is negative 1 ohm. And we've left the inductive reactance at 3 ohms and the real resistance at 4 ohms. So in this case, here's our inductive reactance of 3 ohms. It's the whole length of this line. But we subtract the 1 ohm of capacitive reactance. So now this side of the triangle is only 2 ohms. So when we go through with our Pythagorean theorem here, we end up with the square root of 20 ohms. And our angle is calculated in this way. So here's the more general case for the impedance and the more general case for the direction of the impedance. Now note that it is possible for x sub c to equal x sub l, and in that case the angle would go to 0 and the impedance would just be the resistance of the circuit. So here's our RLC circuit again, and our formula for inductive reactance and capacitive reactance. And note that the magnitude of the inductive reactance will increase with frequency. Remember, omega is 2 pi f. And it would also increase if we increase inductance. Now, capacitive reactance works the opposite way. If the frequency goes up, the reactance goes down. If we increase capacitance, the reactance goes down. Now, when these two reactances are equal and actually cancel out in the circuit, we call that resonance. And at resonance, the magnitude of inductive reactance is equal to the magnitude of the capacitive reactance. So that means omega L is then equal to 1 over omega C. So we can solve for omega, and we end up with 1 over the square root of LC. And since omega is 2 pi f, the resonant frequency is 1 over 2 pi times the square root of LC. So here's our resonant frequency again, given in hertz. Now in my previous video on LC, and there's a link below to it if you missed it, I explore what I call Wonderland, where wonder is spelled with a 1. And by using one full measure of each unit of every variable, we gain some insight that makes things a little more understandable, I think. Now, if we substitute 1 Henry and 1 farad in here, we end up with a resonant frequency of 1 over 2 pi hertz. Now, there's nothing magical about using hertz or a full cycle per second as a measure of frequency. We could say that one full cycle is 360 degrees and break frequency down into degrees per second. Now it turns out there's a real nice angle for measuring cyclical things, and that's the radian. If we take a circle and make this arc length equal to the radius, this angle here is a radian. And it turns out there are 2 pi radians in a circle. So a frequency of 1 over 2 pi hertz is a frequency also of 1 radian per second. And notice that goes along nicely with our Wonderland. And I find this kind of a satisfying solution. In the field of control system analysis, it's common to actually use radians per second as frequency, and bandwidths are also expressed in radians per second. So it's not quite as esoteric as you might think. Okay, here we have a demonstration of the series RLC circuit. Here we have a resistor, a 0.5 microfarad capacitor, and a 100 microhenry inductor. And this circuit's being driven from this oscillator. And I'm displaying here on an oscilloscope the voltage across the inductor on one channel and the voltage across the capacitor on the other channel. And right now we're at the resonant frequency, which is approximately 31 kilohertz. So the two voltages are equal and opposite, and notice they're 180 degrees out of phase there. Now if I raise the frequency, you see one is getting larger and one is getting smaller. And at the higher frequency, the impedance of an inductor goes up, I should say the reactance, so the voltage will go up. And if we lower the frequency, now the voltage across the capacitor is increasing because its reactance is increasing. And again, we can find the frequency where the two waveforms are equal and opposite. And this is showing what the phasor plot is really telling us. I've changed our setup a little bit. I have one of the probes connected across the L and the C, and the other probe is reading the voltage across the resistor. So on our oscilloscope, the upper trace is the voltage across the L and C total, both of them, and the bottom trace is the voltage across the resistor, which shows us that we do have current flowing. Now as I change the frequency, that's going away from the resonant frequency. And now as I approach resonance, notice the voltage across the L and the C combination goes to 0. And if I continue to lower the frequency, you can see it goes back up. So there's what we would call the resonant condition. So since the voltage across the L and C combination is zero and there's current flowing, that means there's a very low impedance. Theoretically, a series L and C at resonance, if the components were perfect, would be 0 ohms. Here I've changed the setup again. In this circuit, the inductor and capacitor are in parallel, and they're in series with a resistor. So with one channel, I'm looking at the voltage across the parallel LC, and the other channel is looking at the voltage across the resistor, which would be proportional to the current. Now on the oscilloscope, the top trace is the voltage across the parallel LC. And I'm going to change the frequency. Right now I'm going up in frequency. And you see the voltage is going down across the LC, the parallel LC. So now I'm going back the other way. And here I'm finding a peak where I'm trying to find the maximum voltage. And notice the current goes down as that voltage goes up. Here, I'll change the frequency again, going up in frequency. You see the current increasing as the voltage comes down. So what's going on here is that at resonance, there's the resonant point, we have a minimum of current. So a parallel LC circuit at resonance is a high impedance. We have high voltage and low current. And theoretically, with perfect components, the voltage would go very high and the current would go very, very low. So this parallel LC circuit is sometimes called a tank circuit when it's used in certain types of applications. So what's going on at resonance, there's just energy being pumped from the capacitor to the inductor and vice versa in a cyclic manner. So in the way it's like a tank storing something. So we have energy flowing back and forth and under a high impedance condition. Okay, here's the same setup with the parallel LC. And this time I'm hitting the circuit with a square wave. And here's our waveform. When the square wave goes positive, we have our tank circuit is ringing at its natural resonant frequency. And then when the square wave goes in the opposite direction, we're taking off here in the other direction. So this is sort of acting like a bell being hit with a hammer, and the circuit is ringing at its natural frequency. Now, I want to show you something else here. This is a piece of copper-clad PC board. It's about 1 inch wide. And I'm going to bring it near the inductor. And I wish I could show the scope and this at the same time. But as I approach the inductor, you see our ringing gets less intense. And that's because of losses induced from the magnetic field of the inductor, inducing eddy currents into the PC board material. So the purpose of this is to just show that inductors are radiating energy all the time, and we have to go to great lengths to prevent the magnetic field of inductors from going places we don't want it to go. Now, there's a lot more to learn about inductors and capacitors, and I'm going to make some more videos on this subject, so be sure to subscribe and hit that like button if you got anything out of this.